I hope you can hear me loud and clear. So I'm excited to invite you for our next session, which is about memory technology, how memory technology is unleashing the potential of AI. Talking about memory technologies, I cannot think of a more accomplished leader than Sumit Sadana. Sumit is the Executive Vice President and Chief Business Officer at Micron Technology, one of the global leaders in memory. Sumit is responsible for company's P&L for all of its business units, as well as corporate strategy, corporate business development, Micron Ventures, and global communications and marketing. Over his career, he has roles ranging from CTO to CFO to GM in companies ranging from in Micron, SanDisk, Freescale Semiconductors, after starting his career as engineer at IBM. Sumit has completed over $40 billion of M&A, and he's on the board of Silicon Labs as a lead director, and also on other nonprofits. He's an alum of Stanford and IIT Kharagpur. And with further ado, let me introduce and welcome Sumit Sadana.
There was a lot of palpable excitement in the halls of one of the most prestigious hospitals on the East Coast of the US, because they were about to start live testing of a new AI software that had been in training for multiple months. This software had been trained on hundreds of thousands of scans to detect cancer amongst patients who had confirmed cases of cancer. And also, it had ingested a lot of scans of patients who were healthy. When they turned this system on and started to work on live diagnostic cases, they created a very good protocol. When the doctor and the AI software agreed on the diagnosis, they would proceed with that diagnosis. But if there was a disagreement, then a second and sometimes a third doctor would step in, assess the situation, and if the doctors were in agreement, then feedback would be provided to the software developers that some tweaks were needed to the algorithm, a mechanism known as the learning feedback provided to the software. Now, a very interesting thing happened because in 9 out of 10 cases, the doctor and the software agreed on the outcome. But in 10% of the cases, there was a disagreement. And when more doctors looked at those scans, they sent some of these patients home because they concluded there was nothing there. And a few months later, some of these patients started to come back with confirmed cases of cancer. And when more research was done, it became clear, well put in the words of the lead scientist leading that effort, that the software was seeing things in the scans, in these high-resolution scans, that were imperceptible to the human eye. The software was reaching 92 to 95% accuracy versus about 86, 87% for doctors. And the software had fewer false positives and false negatives as well, which was, especially for cancer, really, really critical. A few months ago, another interesting publication was made available by the Mayo Clinic. This time, they were able to show that software trained by AI was able to use a 10-second clip of human voice recorded over a smartphone and detect whether that person, using this 10-second clip, had type 2 diabetes. And this detection had the same accuracy as a blood test. And the way this was happening was that the software was able to detect changes in the tenor of a person's voice, comparing it against a database that had been provided to it of 180,000 samples of people with diabetes and without. and it was able to tell with 89% accuracy simply based on that 10-second clip of voice. Once again, the software was able to detect things that were completely imperceptible to the human ear. A third example I just wanted to provide, also in the field of healthcare, is related to proteins. Proteins, as we all know, are the foundation of all human life. Our own body has 20,000 plus proteins that are made up in different strings, different molecules inside the body. And all species taken together on the earth have about 200 million plus unique proteins. And the 3D structures of these proteins are incredibly critical because these 3D structures are what get used to design drugs. The 3D structure of the protein is what latches onto receptors and cells, whether they want to activate or deactivate certain cells and receptors, whether it is for cancer, whether it is for the immune system, and so on. And after 70 years of research, as a human race, we have been able to figure out the 3D structures of about 200,000 proteins, or less than 0.1% of all the proteins that exist. So once again, AI was put to this task, and after ingesting about 100,000 protein 3D structures, within a space of 6 months, starting in early 2022, all 200 million protein 3D structures had been sequenced. And that was made available for free to 500,000 researchers around the world from 190 countries, which these researchers are hailing as the biggest breakthrough since the DNA was sequenced, the human DNA. So all of these examples are clearly showing that we are on to something really, really big. Now, arguably, AI has been around for over 30 years. People have been studying AI, working on AI, researching AI, but something interesting has happened very recently where the pace of progress in AI has become really exponential. Now, exponential functions themselves are a miracle of nature. They don't exist very often. Very often they are man-made. But you have seen some of these examples. Moore's law in semiconductors is one such exponential. You have seen what that has done to the world of technology. Now, today, we stand on the threshold of 4 different exponentials intersecting each other and creating this world of AI that we are all seeing. And I wanted to just walk you through very quickly these 4 incredible exponentials that have come together. The first one is compute power. Now, certainly Moore's law has been at play, but we have also gone from the world of CPUs to the world of GPUs. And you heard earlier today from Jensen, spoke about how much compute capability has advanced in the last 10 years alone using GPUs. But it's not just GPUs alone. It's also the memory subsystem sitting next to the GPU, which has made tremendous strides. In fact, a lot of AI workloads are memory-bound workloads. They are not processor-bound workloads. What that means is, if you want to improve system performance, you actually have to improve the bandwidth between the memory and the processor. Simply improving processor speeds is not going to help, because the processor, if it's faster, is just going to spend more time idly waiting for data from the memory. So this is what has been critical and has been the focus of innovation. So you see here in this picture a GPU next to what is called high bandwidth memory, or HBM. That's the newest innovation in the memory industry. It's the most complex product by an order of magnitude that the memory industry has built, and has been critical in terms of driving higher performance. The next exponential is improvements in algorithms. Now, these take significant step functions from time to time. And in terms of these step functions, you have seen that there was a huge improvement when deep neural networks were started to be used in these algorithms for the first time. That happened and accelerated more than a decade ago. But now, with generative AI, another big leap has happened. And this leap is a transformational leap. And it is going to be the foundation for a lot of new innovations in the future. The next big thing is massive data sets. And data has been exploding, has been growing exponentially. Everyone knows that. But now this has been put to use in training these algorithms, in training these AI programs. And that kind of training is so critical and so important with these massive data sets because it enables AI to learn in ways that are similar to how a human being learns. And the last one is connectivity and the amount of networking that is there around the world, the number of endpoints that are connected, the amount of data all of these endpoints are creating. You have heard about the Internet of Things and the billions of endpoints that are growing around the world. So this is all coming together in this golden age of AI. Micron and our team has had the good fortune of being able to work with some of the leading scientists and researchers in the field of AI, everything from startups to some of the largest companies in the world who are investing heavily in AI. And as we try to put together what is really happening in the field of AI and where is all of this going, it became very clear that the trend in AI is in fact the most important trend for not just the world of technology, but all of humanity. Because it is going to make such big changes to our world that we cannot even begin to fathom. And it all starts with artificial narrow intelligence, or ANI, which has been in place for many years. This ANI is the foundation of everything that you experience today already when you watch movies on Netflix. The recommendations that you get come from artificial narrow intelligence. When you watch YouTube videos or you go to your Facebook feed, the kinds of things that you see are heavily dependent on your own preferences and likes, and that comes from ANI. Now, the big jump is in going from ANI to AGI, or artificial general intelligence. And artificial general intelligence is really the big prize for which everybody is aggressively investing. And AGI refers to a level of human intelligence that is on par with regular human beings in most aspects related to intelligence. Now, obviously, the software cannot do physical actions like a human being can, but in the areas that are cerebral in nature, related to the brain, related to intelligence, related to thinking, this AGI is a huge deal. And we are significantly closer to AGI than most people believe. And I personally think that we will get there in 5 years or less. And this is a view shared by a lot of leading researchers in this field. Now, what happens when you get to AGI? Because now this is another exponential function that is taking shape in front of our eyes. When we get to AGI, we get a level of intelligence. We won't just have a text-based interface with this intelligence. We'll be able to tap into it with voice. We'll be able to hear voice back. There will be bots built with this capability, so they will be able to move around and and be more available than just your PC or your smartphone. So a lot of new innovations will come around. But for those of us who think that human intelligence is a lot more than what you can do with ChatGPT today, there is intuition involved, there is perception involved, there is a level of psychology in human beings, in the way we relate to each other, in the way we support each other in terms of friendships, in terms of relationships. But imagine an AI that is more fun to be with than your friend, or more supportive than your spouse, or more patient than your boss, or more empathetic than your doctor. And perhaps I would say much more knowledgeable than your doctor and far more available and accessible than your doctor even. So these are all things that are coming, and they're coming at us really fast. And the path to AGI is not just based on what we have been able to do thus far with generative AI, but there are lots of innovations in the works that leading companies around the world are investing in. This is just a small sampling of all of the big changes that are coming on the road to AGI. Building hybrid models. Many of you have seen that it is not really easy for generative AI to do basic math sometimes. And so the idea here is you don't have to have basic math be done by generative AI principles. You can use symbolic AI, you can use existing techniques to do math really well. And so you split up the problem, have it be solved in different ways, put it back together, in many ways just like the human brain does, quite frankly. So that's the hybrid model. A lot of advancements in neural networks and algorithms are taking shape. And then there is biological inspired AI. So if you think about the human brain, we have about 100 billion neurons in the brain. These 100 billion neurons have about 100 trillion connections or synapses between them. That is how the magic of the human brain happens. Now, if you look at the number of parameters in these AI models, they are skyrocketing, and the latest models are somewhere in the 1 to 2 trillion range. Now, 1 to 2 trillion parameters in these models versus 100 trillion synapses in the human brain. So obviously, we are just at about 1% of the number of connections that the human brain creates. So there is a lot to do yet, and these models consequently are going to get bigger and bigger and bigger. And the bigger these models get, the more intelligent they get because of the connections and the synapses that we are trying to mimic from the human brain. Now there is enhanced reinforcement learning. We spoke about reinforcement learning with human feedback or RLHF techniques that have been in use for many years. But there are now enhanced capabilities in terms of how to make the software get to the right end result, converge faster, more optimally with sparse feedback so that there is less human interaction involved. It may be at different points in the chain instead of just doing it at the end, but definitely a process which can be made more efficient to minimize and scale up, minimize the time usage by humans and scale up, because you see on the right side, scalability is a big challenge in AI. Power consumption is a big challenge. I mean, you've seen how much power these data centers use. We are at 3% of the world's power consumption in data centers today already. 3% of all the power generated in the world is just going into data centers. By the end of this decade, it will be 8 to 10%. So the amount of power these data centers use is just mind-boggling. Now, compared to that, the human brain uses minimal power. So there is a lot still to be learned about how to mimic the human brain and make things more efficient. The last one is about robotics. Robotics and AI and generative AI and all of these different enhancements to generative AI are all going to come together, and you will start seeing these devices and robots that are far more human-like and far more intelligent over the next few years. And where that is leading us to in another 10 years is artificial superintelligence. And I am very convinced that we are going to get there in a reasonable time frame in that next 10 years after the next 5 years. So we're talking about 15 years from now. And 15 years from now is closer than it appears, right? I mean, we had just 15, 16 years ago the great financial crisis, and we are equidistant from that point to this point where we have artificial superintelligence. So it just gives you a view that the future is a lot closer than it looks. And what is ASI after all? ASI is that point in time where all of the collective wisdom of humanity, not all of the data, not all of the knowledge and insights, but all of the wisdom of humanity gets collected in a single data center. And these algorithms train on that and possess this level of capability that is superhuman in nature. And we are going to get there because the path that has been opened up now, it is only a matter of time, investment, and a few breakthroughs that most researchers have a line of sight to. And of course, a lot of data. So that is absolutely going to change everything around us in society. And it is difficult to think about any part of society, any profession, any business, any way of doing things that is not going to be hugely changed with all of this. Imagine having the capability of every profession you can think of, whether it's a lawyer or a doctor or an engineer, to have a capability at your fingertips that can answer the most complex questions at the click of a button. You'll be able to talk to it and get answers. Pervasive capability to get the deepest human knowledge and wisdom at all times, right? Now, if you want to take a darker view of this, you could say this represents the absolute commoditization of human knowledge, which is a very scary thing for sure. And we'll have to all learn to figure out how to deal with it. So I wanted to change gears a bit and talk a little bit about how are hardware systems and platforms and architectures changing to accommodate what is coming at us. So this is a traditional hierarchy of hardware. You have a processor, it has an SRAM, and it works with DRAM, which is volatile memory, and then you get to flash memory, NAND storage, which is non-volatile and semiconductor-based, and then you get electromechanical storage, which is hard drives. And as you go down from this pyramid, the amount of capacity increases, but latency of access also increases. And if you go up from the bottom, you get higher cost and higher bandwidth. And what is changing now is the DRAM portion of it is becoming much bigger and more complex. You're having high bandwidth memory right at the top, being the critical resource for the processors when you do these AI programs. Then you have a whole bunch of additional data, DDR, all of the data that's being fed to the processor from this traditional DDR memory. And then you have expansion DRAM that is connected via CXL, which is a new protocol and interface. And on the SSD side, you have high-performance SSDs, but SSDs will quickly get to a point where the total cost of ownership is going to be such that you can actually displace a lot of hard drives. Now, the way this looks on a legacy architecture is you have the CPU connected with SSDs and hard drives and through a DDR bus to DRAM. But in the new architecture that has displaced this old one is you have the GPU at the center of the world. This is why you have seen NVIDIA becoming so successful, because they are masters at this. The GPU is at the center of the world, and it's connected with HBM on either side, on all sides actually. And then it connects to a CPU, not necessarily because it needs all of that processing capability, but because the CPU enables it to connect to massive amounts of DRAM, right? So that DRAM access is what is very critical. Now, a less known fact is how much memory is being used in these systems. So I wanted to show you a picture of the latest H200 NVIDIA GPU that is shipping. And next to it, you see 6 stacks of HBM memory, high bandwidth memory. And each of these is not a single chip. Each of these 6 things around it is not a single chip. Each of these is a stack of memory chips. And that stack is 8 die high, meaning there are 8 memory dies stacked on top of each other, and then there are 6 such stacks. In the next generation, we are going to 8 stacks around the HBM. And later on, it will go from a stack of 8 memory chips in each of them to 12, meaning another 50% increase. So already the area of memory that is being used is 7 times, more than 7 times the amount of area of silicon that is there in the GPU. So that's how big this is. And why is there so much need for memory? And I wanted to show you this really interesting data from OpenAI that shows how intelligent these models get when you throw more bigger sizes of models. So on the y-axis, you see the proficiency of these models in being able to understand English. You can create similar graphs for how they actually produce code, right? You can get these models to write code for you. You can create full English prompts, and without knowing any programming today, these models will produce really good quality code. And that capability increases pretty much in line. As you see on the bottom axis is the number of parameters. So as you get to 1 trillion parameters, you start to see that hockey stick getting closer to 90%. Now, how do you get from 90% to 100% is, again, you have to dramatically increase the amount of data that these models ingest. And that is what is on a path to be done. But what happens to the memory that is needed when you go into these models in this fashion? This has already become vertical. On the y-axis, the amount of memory, again on the x-axis, the same model sizes. But this is only going through GPT-3 and Turing. Now, if I want to draw what GPT-4 took, I have to actually change this y-axis on this model, because that's where GPT-4 was. So you can see how massive these models are. And these models are going to be used in applications that will change everything we know about our society. Now, many of these things are coming at us. They're already there in the data center. Now you're going to see, starting late this year, PCs and smartphones being introduced with small version of large language models. So they can do interesting things on your PC and phone. And PCs and phones already have some of this capability today. For example, when you take a picture from your smartphone, there is already an AI engine that figures out how to optimize that picture through 1 million different permutations and combinations before it gets saved on your phone. So there is already AI in a lot of different places, and it is just going to be more so. This is actually a real Copilot search. It's not made up. So AI apparently knows something. I'll just end with a couple of thoughts around Micron Ventures. We have a very vibrant entrepreneurial community here, and I just wanted to mention that we have a really nice set of capabilities to work with founders and startups in the areas of artificial intelligence, new compute architectures, as well as in sustainability. There's a sampling of a few companies that we have in our portfolio. There's many more. But sustainability is a big thing for us because we have a massive operational footprint to manufacture all of these things. And we have been using AI in our fabs in a very big way. Micron has won a number of awards around the world as being the showcase fabs for the use of AI. And you can see here the results in productivity that have come from all of that usage and pioneering work, candidly, in AI when it comes to operations. Another thing that we are very proud of, we have had an operation in India for a number of years, but Micron became the first company, the first semiconductor company in the world to make a significant commitment to India in terms of an investment in semiconductors through a $2.75 billion investment that we announced. That's going to result in thousands of jobs, but more importantly, it's going to kickstart the ecosystem of semiconductors in India, which is going to be a huge deal. I wanted to just end with one last slide, which is for all of the great promise of AI, there is a lot of work ahead. There are significant challenges AI is going to create for society, and we have to be ready for it. They are too important to gloss over for sure. Any one of these items that you see on this slide can take up an entire hour of discussion. These are all super critical, not the least of which includes, what happens to human connections and loss of human intuition and critical thinking when you give them tools, when you give humanity tools like the ones that are coming at us with AI. So lots to think about, lots to do, and we look forward to certainly being part of the conversation, partnering with companies and organizations and customers and society to make it a better world. Thank you.